Hello everyone, this is Professor He. Nice to see you again. The topic of this task is about the Carnot vapor cycle. We all know from experience that heat flows in the direction of decreasing temperature, that is, from high temperature regions to low temperature ones. This heat transfer process occurs in nature without requiring any devices. The reverse process, however, cannot occur by itself. The transfer of heat from a low temperature region to a high temperature one requires special devices called regenerators. Another device that transfers heat from a low temperature medium to a high temperature one is the heat pump. A major application area of thermodynamics is regeneration, which is the transfer of heat from a lower temperature region to a higher temperature one. Devices that produce refrigeration are called refrigerators, and the cycles on which they operate are called refrigeration cycles. The most frequently used refrigeration cycle is the vapor compression refrigeration cycle, in which the refrigerant is vaporized and condensed alternately and is compressed in the vapor phase. Another well-known refrigeration cycle is the gas refrigeration cycle, in which the refrigerant remains in the gaseous phase throughout. Other refrigeration cycles include cascade refrigeration, where more than one refrigeration cycle is used, and absorption refrigeration, where the refrigerant is dissolved in a liquid before it is compressed. Now, let's talk about the refrigerators and heat pumps. Refrigerators and heat pumps are essentially the same devices. They differ in their objectives only. The objective of a refrigerator is to maintain the refrigerated space at a low temperature by removing heat from it. Discharging this heat to a higher temperature medium is merely a necessary part of the operation, not the purpose. The objective of a heat pump, however, is to maintain a heated space at a high temperature. This is accomplished by absorbing heat from a low temperature source such as well water or cold outside air in winter, and supplying this heat to a warmer medium such as a house, as shown in the right figure. The performance of refrigerators and heat pumps is expressed in terms of the coefficient of performance defined as. Notice that both COP refrigerator and COP heat pump can be greater than 1. We can find this relation implies that the COP heat pump is greater than 1 since COP refrigerator is a positive quantity. That is, a heat pump functions at worst as a resistance heater, supplying as much energy to the house as it consumes. In reality, however, part of QH is lost to the outside air through piping and other devices, and COP heat pump may drop below unity when the outside air temperature is too low. When this happens, the system normally switches to the fuel or resistance heating mode. Now, let's talk about the refrigerator with a reversed color cycle. Recall from Project 3 that the color cycle is a totally reversible cycle that consists of two reversible isothermal and two isentropic processes. It has the maximum thermal efficiency for given temperature limits, and it serves as a standard against which actual power cycles can be compared. Since it's a reversible cycle, all four processes that comprise the color cycle can be reversed. Reversing the cycle does also reverse the directions of any heat and work interactions. The result is a cycle that operates in a counterclockwise direction on a TS diagram, which is called the reversed color cycle. A refrigerator or heat pump that operates on the reversed color cycle is called a color refrigerator or a color heat pump. Consider a reverse color cycle executed within the saturation dome of a refrigerant, as shown in Figure 12.9. The refrigerant absorbs heat isothermally from a low temperature source at T2 in the amount of Q2, is compressed isentropically to state 2, rejects heat isothermally to high temperature sink at T0 in the amount of Q1, and expands isentropically to state 4. The refrigerant changes from a saturated vapor state to a saturated liquid state in the condenser during process state 2 to state 3. The coefficient of performance of colored refrigerators is expressed by definition and is in terms of temperatures as. Notice that COP increases as the difference between the two temperatures decreases, that is, as TL rises or TH falls. Generally, TH is the environmental temperature T0 for refrigerators. Similarly, a heat pump working in a reverse color cycle between TH and TL is shown as. The coefficient of performance of heat pumps is expressed in terms of temperatures as. The reversed color cycle is the most efficient refrigeration cycle operating between two specified temperature levels. Therefore, it is natural to look at it first as a prospective ideal cycle for refrigerators and heat pumps. If we would, we certainly would adapt it as an ideal cycle. As explained later, however, the reversed Carnot cycle is not a suitable model for refrigeration cycles. The two isothermal heat transfer processes are not difficult to achieve in practice, since maintaining a constant pressure automatically fixes the temperature of a two-phase mixture at the saturation value. Therefore, process 4-1 and 2-3 can be approached closely in actual evaporators and condensers. However, process 1-2 and 3-4 cannot be approximated closely in practice. This is because process 1-2 involves the compression of a liquid-vapor mixture, which requires a compressor that will handle two phases, and process 3-4 involves the expansion of high moisture content refrigerant in a turbine. It seems as if these problems can be eliminated by executing the reverse Carnot cycle outside the saturation region. But in this case, we have difficulty in maintaining the isothermal conditions during the heat absorption and heat rejection process. Therefore, we conclude that the reverse Carnot cycle cannot be approximated in actual devices and is not a realistic model for refrigeration cycles. However, the reverse Carnot cycle can serve as a standard against which actual refrigeration cycles are compared. Okay, that's all for this task. Thank you very much and see you next time.